Most people picture the Big Bang as a giant explosion in space, but that's not quite right. Space itself began to stretch into existence, expanding from an unimaginably hot and dense state, carrying everything with it. Oliver, what does this distinction truly mean for our understanding of the universe's origin?
It means the universe wasn't born into a pre-existing void. Instead, the room itself, space, began to grow. From that initial, incredibly hot and dense state, it expanded, cooling as it did. The universe was far too extreme for atoms, stars, or even ordinary light as we know it to exist back then. It was a chaotic sea of particles and radiation, changing at an astonishing speed. As it cooled, tiny density differences began to form, and these would eventually become the galaxies and stars we see today. So when we talk about the beginning of the cosmos, we're really discussing the birth of distance, time, structure, and possibility.
The birth of time and structure. That's a profound thought. It makes me think of the idea that every atom in our bodies was forged inside ancient stars. It implies a direct personal connection to that cosmic beginning.
Absolutely. The calcium in your bones, the iron in your blood, the oxygen you're breathing, none of it was made on Earth. Lighter elements formed in the early universe, but many heavier ones required the intense pressure and heat inside stars. They fused atoms together in their cores. When massive stars ended their lives, they exploded, scattering those essential ingredients into space. This enriched material then gathered into new stars, planets, and eventually living things. We're not separate from the universe, we're made from its older chapters. Every heartbeat relies on matter that once burned in distant suns.
And that connection extends to how we observe the universe. We're always looking into the past, aren't we? Light travels at an incredible speed, yet it still needs time to cross the vast distances.
Precisely. The moon appears as it was just over 1 second ago. The sun, more than 8 minutes ago. A star hundreds of light years away is showing us a version of itself from centuries in the past. With powerful telescopes, astronomers can look so far across space that they're seeing galaxies as they were billions of years ago, when the universe was far younger. It makes astronomy unique. The sky isn't just a place, it's a record. Every distant point of light is a message that left long before it reached our eyes.
That idea of time being relative, or stretched, also comes up with black holes. The source mentions they can slow time almost to a standstill. That feels counterintuitive. How can time itself bend?
It's a real effect predicted by relativity. Near a black hole, gravity becomes so intense it actually changes the flow of time. The closer an object gets to a strong gravitational field, the slower its clock runs compared with clocks farther away. For an outside observer, something falling into a black hole might appear to freeze and fade away. But for the falling object, time continues normally. This shows time isn't a universal, unbending rhythm. It can stretch with gravity and motion, behaving differently depending on your position in the universe.
And much of this universe we can't even see. Dark matter, dark energy. How do we even know they're there if they don't interact with light?
We infer their existence through their gravitational effects. For dark matter, galaxies rotate as if held together by far more mass than we can visually account for. It also bends light from distant objects. Dark energy is even more mysterious, linked to the accelerating expansion of space itself. Together, these invisible components shape the universe on the largest scales. It's humbling to realize that nearly everything we study directly is just the visible edge of a much deeper, unseen reality.
It is, and the sheer scale of the visible universe is mind-boggling. The idea that there might be more stars than grains of sand on Earth, that's almost too vast to comprehend.
It truly is. Our own Milky Way galaxy holds hundreds of billions of stars, and the observable universe contains billions, perhaps even trillions of galaxies. Some are grand spirals, some faint dwarfs, some ancient swarms. When astronomers estimate the total, it surpasses every grain of sand on every beach and desert across our planet. Yet each star is unique, a sun with its own history, chemistry, and potential planetary systems. Some live briefly and explode, others glow steadily for trillions of years. The night sky might look sparse, but we're gazing into an immense ocean of suns.
That ocean includes some truly strange worlds, like rogue planets that wander without a star. What makes a planet simply drift through interstellar space?
They can form in a couple of ways. Some may have formed around stars and then been ejected by gravitational interactions with larger planets or passing stars. Others might have formed directly from collapsing clouds of gas and dust, similar to small failed stars, rather than orbiting a sun. Without sunlight, their surfaces are incredibly cold, but some could retain internal heat from their formation or radioactive decay. A few might even hide buried oceans beneath thick ice crusts. They remind us that space holds not only orderly systems, but also lost wanderers, each carrying its own sealed history.
Speaking of wandering, our own galaxy, the Milky Way, isn't as calm as it appears. It's colliding with other galaxies, isn't it?
That's right. It's surrounded by smaller companion galaxies that are being stretched and absorbed by gravity. The Sagittarius dwarf galaxy, for example, is already being torn apart as it passes through the Milky Way, but it's not a violent, destructive collision in the way we might imagine. Space is so vast that individual stars rarely collide. Instead, it's a slow, ghostly process where streams of stolen stars arc around our galaxy. These encounters help build the Milky Way over time, adding stars and gas, reshaping its structure over billions of years. Our home galaxy is still growing and changing.
And even the Moon, our closest celestial companion, is slowly drifting farther away from Earth. It's not a static relationship.
Indeed. Each year, it moves away by about the width of a few fingernails. This is due to tidal forces. As Earth rotates, the Moon's gravity creates tidal bulges in our oceans. Because Earth spins faster than the Moon orbits, these bulges slightly tug the Moon forward. That tiny gravitational pull transfers energy to the Moon, gradually pushing it outward, while Earth's rotation slows by a small amount. Long ago, the Moon was much closer and tides were stronger. Far in the future, it will appear smaller in the sky. This slow separation is a subtle reminder that even the most familiar celestial relationships are constantly evolving, measured not in drama but in cosmic patience.
The phrase, "space is not empty," also comes up, which seems counter to the popular image of a vacuum. What's actually out there between the stars?
It's far from a perfect vacuum. Space contains thin gas, drifting dust, magnetic fields, radiation, and streams of charged particles from stars. Even seemingly vacant regions hold faint traces of matter spread across enormous distances. Quantum physics adds another layer. What we call empty space is filled with fields that fluctuate and can give rise to particles. Around Earth, invisible magnetic shields guide solar particles into auroras. Between galaxies, tenuous material stretches through the cosmic web. The emptiness of space is a restless stage where forces pass, light travels, and the universe quietly continues its work.
It's fascinating how many of these seemingly empty or distant phenomena are tied to us. Even the Sun, which looks so steady, loses millions of tons of mass every second.
That's its power source. In the Sun's core, hydrogen atoms fuse into helium under immense pressure and heat. A tiny amount of mass is lost in each fusion reaction, and that missing mass becomes energy, as Einstein showed us. That energy streams outward as sunlight, warming our oceans, driving weather, feeding plants, and making almost all life possible on Earth. Even though it converts millions of tons of its own substance into energy every second, it has enough fuel to shine for billions more years. Its brilliance isn't a surface flame, it's matter becoming light in its heart.
And Jupiter, our solar system's giant, almost became a star itself. What stopped it?
It's true. Jupiter is immensely massive, containing more mass than all other planets combined. But it never gathered quite enough material to ignite nuclear fusion, which is what powers true stars. Deep inside, its pressure squeezes hydrogen into strange forms, including metallic hydrogen, which contributes to its enormous magnetic field. Jupiter even gives off more heat than it receives from the Sun, residual warmth from its formation and slow contraction. If the early solar system had provided just a bit more gas, it might have become a small star. Instead, it remains a colossal planet, a guardian of its moons and mysteries.
Another striking image is Saturn's rings. They look so grand and solid, but you're saying they're actually incredibly thin.
Yes, far thinner than most people imagine. While they're wide enough to span a huge distance around Saturn, their thickness is surprisingly small, in many places only tens of feet to perhaps a few stories high. They're made of countless icy particles, from tiny grains to boulders, all orbiting in a delicate, flattened disk. The rings aren't solid or permanent. Gravity from moons shapes gaps in waves, and over time, ring material slowly rains down onto Saturn. What appears eternal is, on cosmic scales, temporary, a magnificent feature we're fortunate to observe while it still shines.
That impermanence extends to other planets too. Venus, for example, has a day longer than its year, and it spins backward. Why such extreme differences from Earth considering its similar size?
Venus truly is alien. Its rotation is so slow that one full turn on its axis takes longer than its entire orbit around the Sun, and it spins clockwise, opposite to most planets, so the Sun would rise in the west and set in the east through its thick clouds. The surface is hidden under a crushing carbon dioxide-rich atmosphere hot enough to melt lead. Its slow and retrograde rotation might have been shaped by ancient collisions, tidal forces, or the drag of its dense atmosphere. It's a stark reminder that even neighboring worlds can start with similarities but end up profoundly different.
And on Mercury, the closest planet to the Sun, we find ice hiding in permanent shadow near its poles. That sounds like a contradiction.
It does, but Mercury has almost no atmosphere to spread heat around. So while its dayside bakes, deep crater floors near the poles never receive direct sunlight and remain intensely cold. Over vast stretches of time, water molecules delivered by comets, asteroids, or internal processes could migrate to these cold traps and freeze. Radar observations confirm bright deposits consistent with water ice. Mercury is a world of sharp contrasts, a scorching landscape next to shadows preserving frozen material for eons.
Mars, too, has these surprising contrasts. It's cold and dusty today, but it clearly once had rivers, lakes, and even a northern ocean. What happened to all that water?
Its surface carries undeniable traces of a wetter past, branching valleys, dried lake beds, river deltas, and minerals that form in the presence of water. Some ancient regions look as though streams flowed across them for long periods. While the extent of a northern ocean is still debated, the evidence for liquid water is strong. The planet lost much of its atmosphere over time, making it difficult for stable surface water to persist. But the old terrain remains like a fossilized memory, making Mars a compelling world in the search for ancient habitability.
Uranus spins sideways as if something knocked it over. Is that what happened? A massive impact?
That's the leading idea. Most planets rotate with their poles roughly upright relative to their orbit. Uranus, however, rolls around the Sun almost on its side, leading to extreme seasons where each pole faces the Sun for decades. A massive impact early in its history is the most probable explanation for this unusual tilt. Another possibility involves complex gravitational interactions. Whatever the cause, it left us with a world that tells a story of the violent early history of planetary formation, when collisions could rewrite the fate of entire worlds.
Then there's Neptune, with winds faster than the speed of sound. How does a planet so far from the Sun generate such furious weather?
It's one of the great mysteries. Neptune receives only a tiny fraction of the sunlight Earth does, yet its atmosphere is astonishingly active, with clouds racing at supersonic speeds. The energy source isn't fully understood, but Neptune radiates more internal heat than it receives from the Sun, and this heat may help stir its atmosphere. Methane in the upper air gives it its deep blue color, and massive dark storms can form and vanish. At the edge of the planetary realm, where cold dominates, Neptune refuses to be still. It's distant, frozen, and violently alive with weather.
Pluto, too, surprised us when New Horizons flew past, revealing mountains made of water ice. How does water ice become a mountain?
On Earth, water ice melts readily, but on Pluto, in its extreme cold, water ice behaves like hard bedrock. It can stand as mountain ranges. Softer ices, like nitrogen ice, flow more like glaciers across its plains. One famous heart-shaped region contains a geologically young, smooth basin with slowly churning ice. Pluto is layered, active, and strange, proving that even small worlds at the edge of the solar system can hold landscapes of breathtaking complexity, challenging our assumptions about what ice can do.
Moving to moons, Titan has rivers and lakes of liquid methane. Does that imply similar cycles to Earth, just with different chemistry?
Yes, in a way. Saturn's largest moon has a thick atmosphere, haze, weather, dunes, and river channels. But because it's so cold, methane and ethane exist as liquids. They fall as rain, carve channels, gather in lakes, and evaporate back into the sky, completing a methane cycle similar to Earth's water cycle. From above, some polar regions look almost eerily familiar with shorelines. Beneath its icy crust, Titan may even hide an ocean of liquid water mixed with other compounds. On Titan, chemistry writes a different version of weather, where hydrocarbons form the rivers and water ice is the rock.
And Europa, Jupiter's moon, is thought to hide a salty ocean beneath its frozen shell. Is this why it's considered such a prime candidate in the search for life?
Exactly. Europa appears as a cracked white sphere, and beneath that frozen exterior, many scientists believe there's a global ocean of liquid water. Tidal forces from Jupiter flex Europa as it orbits, generating internal heat that could keep the water from freezing solid. The surface cracks and shifting ice patterns suggest movement from below. If this ocean touches a rocky seafloor, chemical reactions could provide energy sources, much like deep-sea vents on Earth. Europa is compelling not because it looks like Earth, but because it may hold one of life's essential ingredients, liquid water, in vast hidden abundance.
Even more dramatically, Enceladus, another moon, sprays ocean water directly into space. That seems like a dream for scientists, getting a direct sample.
It's incredible. Saturn's small moon stunned scientists when spacecraft observed plumes erupting from fractures near its south pole. These geysers release water vapor, ice grains, salts, and organic molecules from beneath the surface, spraying outward and feeding one of Saturn's faint rings. This provides a direct sample of the moon's interior without needing to drill. Evidence points to a subsurface ocean in contact with a rocky core, which is crucial because rock and water can exchange chemistry, potentially creating conditions supportive of complex reactions. Enceladus appears cold and bright, but beneath its crust it may be warm enough for liquid water to persist.
Io is the most volcanically active world we know, constantly pulled and squeezed by Jupiter's gravity. How does its volcanism compare to Earth's?
It's fundamentally different. On Earth, volcanism is driven by internal heat and plate tectonics. On Io, it's powered by those intense tidal forces from Jupiter and its other moons. This flexing generates extreme internal heat, resulting in a surface covered with volcanoes, lava flows, and sulfur-rich deposits. Some eruptions launch material hundreds of miles high. Its surface changes rapidly, with new deposits covering older terrain, painted in vivid yellows, oranges, and whites by sulfur. Io demonstrates that a moon doesn't need to be large to be geologically fierce.
And then Ganymede, larger than the planet Mercury, yet still a moon. What makes it so exceptional?
Its size alone places it in planetary conversation. It's the largest moon in the solar system, only slightly smaller than Mars. Orbiting Jupiter, it has a surface of ice and rock with bright grooves and impact scars. What's truly remarkable is that Ganymede has its own magnetic field, a feature no other known moon possesses in the same way. There may be layers of liquid water between different forms of ice beneath its crust. Its interior is differentiated, meaning heavier materials sink to the core. Ganymede is a complex world with its own geology, magnetism, and possible hidden oceans.
Triton, Neptune's largest moon, orbits backward. That's a strong indicator it didn't form there, isn't it?
It is. Its unusual retrograde orbit strongly suggests it was captured from the outer solar system, likely from a population of icy bodies beyond Neptune. This capture would have been a dramatic event, probably disturbing or destroying any pre-existing moons. Today, Triton is a cold world with a thin nitrogen atmosphere and geyser-like eruptions that send dark material across its surface. Its orbit is slowly changing, and far in the future, Neptune's gravity might even tear it apart, potentially forming new rings. Triton feels like an adopted world with a turbulent past, carrying the chemistry of distant origins.
Shifting to smaller bodies, the asteroid belt is often portrayed as a crowded obstacle course in science fiction, but the reality is quite different.
Indeed, while it lies between Mars and Jupiter and contains millions of objects, the distances between them are usually vast. A spacecraft can pass through without constant dodging. The belt likely holds leftover building blocks from the early solar system that never formed a planet, largely because Jupiter's gravity stirred the region too strongly. Its objects range from tiny fragments to large bodies like Vesta and Ceres, composed of rock, metal, or carbon-rich materials. It's more like a preserved construction yard, offering clues about how worlds were assembled.
And Ceres, the largest object in that belt, may contain more water than many icy worlds, which is a surprising find for a body in the inner solar system.
It is. Classified as a dwarf planet, Ceres has revealed bright salt deposits, clay minerals, and evidence of water playing a crucial role in its history. Beneath its surface, it may contain a mixture of rock, ice, salts, and possibly pockets of briny liquid that have survived for a long time. Some bright regions appear to be formed when salty material rises from below. Ceres quietly preserves a record of how water and minerals moved through the young solar system, even in the rocky inner regions.
Comets are often described as dirty snowballs, but the source calls them frozen archives. What makes them so valuable scientifically?
They truly are archives, formed in the early solar system from ice, dust, and organic compounds far from the sun's heat. Many have spent billions of years in deep cold, barely changed since planets were taking shape. When a comet approaches the sun, its ice vaporizes, carrying dust to form its spectacular coma and tail. But that display is secondary to their scientific importance. Comets preserve the chemistry from the solar system's beginning, revealing complex molecules and ancient grains, offering clues about how water and carbon-rich materials traveled between worlds. They are time capsules.
Halley's Comet has been observed by humans for centuries, becoming a powerful link between astronomy and our history.
It's one of the few objects that connects us so directly. Halley's returns to the inner solar system roughly every 76 years, meaning many generations have witnessed it. Ancient observers recorded its appearances, often as omens, long before its orbit was understood. Edmund Halley then studied earlier sightings, realizing they were the same object. Its predictable reappearance transformed a mysterious sky event into a triumph of celestial mechanics, linking people across time as they watched the same icy body sweep back from the dark.
And on a more local scale, meteor showers happen when Earth crosses old comet trails. It's not just random sparks in the sky.
That's right. Many meteor showers occur when Earth passes through streams of dust left behind by comets. As these tiny grains, often no larger than pebbles, enter our atmosphere, they burn up high above the ground, creating those bright streaks of light. Because Earth crosses the same debris paths annually, some meteor showers, like the Perseids or Leonids, return predictably, connecting us to these ancient comet materials. Each streak is a tiny fragment of cosmic history, briefly visible as our planet sweeps through a dusty path around the sun.
The International Space Station circles Earth every 90 minutes. It sounds almost stationary from our perspective, but it's really moving incredibly fast, constantly falling around the Earth.
Indeed, it's not floating still, it's falling around Earth at such speed that it continually misses the ground. In a single day, astronauts on board see 16 sunrises and 16 sunsets. Traveling at roughly 17,000 miles per hour, yet inside, crew members drift, conduct experiments, and sleep strapped gently in place. It's a laboratory, a home, and a lookout post all at once, transforming Earth into a moving world without borders, turning silently beneath them.
And astronauts even grow taller in orbit because their spines relax. What does this tell us about gravity's constant influence on us?
It reveals how deeply gravity is written into our biology. On Earth, gravity constantly compresses our spines, making us slightly shorter at night. In orbit, without that downward pull, the discs between vertebrae expand and the spine lengthens. Some astronauts gain a little height, though it's temporary. This is part of a larger picture. Our bodies evolved with weight, pressure, and resistance. Without these forces, muscles weaken, bones lose density, fluids shift, and balance systems become confused. Spaceflight clearly demonstrates how fundamental gravity is to our physical being.
And spacesuits are essentially tiny spacecraft built around human bodies. The engineering involved must be immense.
They are far more than clothing. A suit used for spacewalks must create a survivable world in a vacuum, with no breathable air, no normal pressure, and extreme temperature swings. Inside, it provides oxygen, removes carbon dioxide, regulates heat, maintains pressure, and protects against tiny, high-speed particles. Gloves need to be flexible for tools yet strong enough for vacuum, and helmets offer visibility while shielding from harsh sunlight. Every joint must allow movement without leaking. When an astronaut steps outside, the suit becomes a personal life support system, a fusion of engineering and biology, carrying a small piece of Earth into space.
Rockets work by throwing mass backward with enormous force, not by pushing against the air, which explains why they work in space.
It's all about momentum. A rocket doesn't push against air. It moves because for every action, there's an equal and opposite reaction. When hot gas blasts out of the engine in one direction, the rocket is pushed in the other. It's the same principle you see when a balloon shoots across a room after you let it go. Rocket engines burn fuel and oxidizer to create a fierce, directed exhaust, moving at tremendous speed. The vehicle must carry nearly everything it needs, including the oxygen for combustion, which is why rockets are mostly propellant at launch, governed by the brutal math of escape.
The first footprints on the moon may last millions of years, unlike anything on Earth. Why such permanence?
The moon has no weather as we know it. No wind, no rain, no flowing air, and no living surface to cover a mark. When astronauts stepped onto the lunar soil, their boots pressed patterns into fine, dusty material created by billions of years of impacts. Those prints remain exposed to space, slowly altered only by micrometeorites, radiation, and the faint effects of the solar wind. They won't last forever, but they may endure for immense stretches of time, a single human step becoming part of the moon's surface history.
And that lunar dust smelled like burnt gunpowder to returning astronauts, an unexpected sensory experience.
Since the moon has no air, astronauts couldn't smell it outside. The surprise came after they returned to the lunar module. Fine dust clung to their suits and equipment, then entered the cabin. Once exposed to oxygen and moisture inside, it gave off a sharp smell that several astronauts compared to spent gunpowder. The dust was also clingy and troublesome, made of jagged grains from endless impacts, not smoothed by water and weather like on Earth. It made a silent, distant world suddenly immediate, as if the moon had followed them inside.
From space, Earth's atmosphere glows faintly. What causes this air glow?
Airglow comes from atoms and molecules high in the atmosphere absorbing sunlight during the day, then releasing that energy as faint light at night. It's different from city lights or auroras. To astronauts, this glow appears as delicate bands of green, red, or golden color tracing Earth's curve. It highlights something easily forgotten from the ground. Our atmosphere isn't an infinitely thick shield. It's a slender layer wrapped around the planet, thin compared to Earth's size, yet absolutely vital to everything alive below.
Auroras, the northern and southern lights, are another visible connection to space. How do solar particles interact with Earth to create them?
The sun constantly releases charged particles into space. Most would be dangerous if they reached the surface directly, but Earth's magnetic field guides many of them toward the polar regions. There, they collide with atoms and molecules high in the atmosphere. Oxygen and nitrogen absorb this energy and then release it as shimmering light, greens, reds, purples, and blues rippling across the sky. While they look soft, they're connected to powerful space weather. Strong solar storms can disturb satellites, radio signals, and power systems, demonstrating Earth isn't isolated from the sun's activity.
And the Van Allen belts trap charged particles around Earth. They're an invisible part of Earth's defense system, aren't they?
They are regions where energetic particles, many from the solar wind or cosmic rays, are caught by Earth's magnetic field. Once trapped, they spiral along magnetic field lines and bounce between northern and southern regions. For spacecraft, this environment is critical, as electronics can be damaged and astronauts must limit exposure. The belts form a vast, restless region around our planet, an invisible but crucial part of Earth's protective system.
Even satellites can fall from orbit because space isn't a perfect vacuum. A tiny bit of air resistance makes a difference over time.
That's correct. While orbit seems like a vacuum near Earth, there are still extremely thin traces of atmosphere. A satellite moving through that thin gas experiences a tiny amount of drag. Over time, this drag steals orbital energy, causing the satellite's path to shrink. It sinks lower, where the air is slightly thicker and the drag increases further. Without correction, it eventually re-enters the atmosphere and burns up, breaks apart, or falls in controlled fragments. Falling from orbit isn't a sudden drop, it's a slow surrender to the last wisps of Earth's air.
It's interesting to consider that stars are born inside cold clouds of gas and dust. We associate stars with fire, but their birthplaces are far from fiery at first.
Their birthplaces are indeed cold, dark molecular clouds, where gas and dust drift together. Gravity slowly gathers denser pockets within these clouds. As a pocket collapses, it spins, flattens, and heats at the center, becoming a protostar hidden behind dusty material. Around it, a disk can form where planets may begin to assemble. Eventually, if the core becomes hot and dense enough, hydrogen fusion starts and a new star ignites. Stars condense out of cold material, awakening from shadow into brilliance.
And a star's color reveals its temperature, but it's the opposite of what we might expect. Red is cooler, not hotter.
That's a common misconception. A red star is relatively cool on the stellar scale, while a blue star burns at far higher temperatures. Cooler stars glow red or orange. Stars like our sun shine yellow-white, and the hottest stars blaze blue-white, emitting intense ultraviolet radiation. This color gives astronomers vital information about a star's mass, lifespan, energy output, and even conditions around its planets. Blue stars burn hotter and die faster, while smaller red stars use their fuel slowly and carefully, lasting far longer than the current age of the universe.
Some stars even pulse like cosmic hearts in steady rhythms. What causes that?
These pulsating stars change because internal forces fall in and out of balance, causing them to grow brighter and dimmer in measurable patterns. Certain kinds, like Cepheid variable stars, are incredibly valuable because their rhythm reveals their true brightness. This allows astronomers to measure vast distances across space. A pulsing star essentially becomes a cosmic measuring tool.
When massive stars die, they can become neutron stars, which spin hundreds of times per second and are incredibly dense.
Yes, their core collapses into an incredibly compact neutron star, spinning faster as it shrinks, much like a skater pulling in their arms. Some neutron stars pack more mass than the sun into a sphere only about the size of a city. A teaspoon of neutron star matter would outweigh a mountain. It would weigh billions of tons if brought to Earth. Pulsars are rotating neutron stars that sweep beams of radiation like lighthouse signals, and if a beam crosses Earth, telescopes detect a regular, precise pulse. Magnetars, a type of neutron star, have magnetic fields trillions of times stronger than anything we typically encounter on Earth, producing high-energy flares powerful enough to affect our upper atmosphere from across vast distances.
And the ultimate stellar death event, supernovas, which can outshine entire galaxies for a short time.
For days or weeks, a supernova may shine brighter than the combined light of billions of ordinary stars in its galaxy. They're destructive, but also incredibly creative, scattering newly forged elements like heavy metals into space, seeding future worlds with the chemistry necessary for mountains, seas, and life. Even gold may form when neutron stars collide in events called kilonovas. White dwarfs, the glowing cores of dead stars, can even explode as supernovas after stealing gas from companion stars, becoming bright enough to help map the universe. Our sun, for instance, will one day become a red giant, then fade into a white dwarf, an Earth-sized ember holding the memory of all the light it gave.
It's all part of the vast cosmic cycle, with stars being born in nebulas, those glowing clouds of gas.
Precisely, star clusters can hold thousands of stars born together, acting as cosmic nurseries. Nebulas glow because nearby stars excite their gases, painting the sky with physics made visible. Dark nebulae, on the other hand, hide newborn stars behind curtains of dust, sealed chambers where new suns are forming.
And at the center of our Milky Way, there's a supermassive black hole.
That's Sagittarius A with the mass of millions of suns. Black holes aren't cosmic vacuum cleaners. Their gravity behaves like any other object of the same mass from afar. Light can even orbit a black hole before escaping in what's called the photon sphere. Hawking radiation suggests black holes may slowly evaporate over unimaginably long timescales, and the detection of gravitational waves, ripples made by moving space-time, from colliding black holes in 2015 meant humans hadn't just seen the universe, we had heard its deep structure move.
Space-time bending around mass, gravity traveling at light speed. It even affects our everyday lives, like GPS systems.
Indeed, time passes slightly faster on satellites than on Earth, a fact built directly into GPS technology. It's a real-world application of Einstein's relativity. And circling back to the Big Bang, it wasn't an explosion into empty space, it happened to space itself. Ancient microwave light, the afterglow of a time when the cosmos first became transparent, still fills the entire universe.
The universe continues to evolve, with galaxies growing by merging, and Andromeda moving towards the Milky Way.
That merger is expected billions of years from now. Future astronomers may actually see far fewer galaxies as cosmic expansion accelerates, stretching old light into redder wavelengths, making distant galaxies harder to observe. Dark energy appears to be speeding up this expansion, and dark matter shapes galaxies without giving off any light of its own. The cosmic web links galaxies in vast invisible threads, forming a great network rather than a smooth spread of lights. Galaxies come in many shapes: spirals, ellipticals, and irregular clouds, each one a biography written by gravity.
And quasars are powered by hungry supermassive black holes.
Some blast jets longer than the galaxies themselves. The earliest galaxies formed surprisingly soon after the Big Bang, and galaxy clusters are the largest structures held together by gravity, while cosmic voids stretch across hundreds of millions of light-years in between. The observable universe isn't the whole universe. Space may be infinite beyond our cosmic horizon, with no known center or edge.
The sheer variety of exoplanets also highlights this. Worlds that might rain molten glass or have vast interiors of diamond or orbit two suns at once.
We found thousands of them. Some are hot Jupiters scorching around their stars, some are hotter than certain stars themselves. Carbon-rich planets could have diamond interiors, ocean planets might be covered by seas thousands of miles deep, and super-Earths are surprisingly common everywhere except in our own solar system. Rogue planets may even outnumber stars in the galaxy, and some worlds could orbit within the habitable zones of patient, long-lived red dwarfs. The James Webb Space Telescope, which unfolded like origami in space, is pushing these boundaries, allowing us to study starlight filtered through alien atmospheres to search for the chemical fingerprints of distant worlds.
Telescopes are pushing these boundaries, allowing us to study starlight filtered through alien atmospheres.
Exactly, searching for the chemical fingerprints of distant worlds. Hubble revealed galaxies where darkness once seemed empty. Radio telescopes listen to cold hydrogen between stars, and space probes have even touched the outer atmosphere of the Sun itself. Voyager 1 carries human sounds beyond the solar system, a golden record drifting into the dark. New Horizons revealed Pluto as active and complex, and asteroid samples can reveal chemistry older than Earth. Future telescopes may search nearby worlds for signs of life, perhaps not forests or oceans, but a faint chemical imbalance in distant air, enough to change human history.
Outer space keeps proving reality is stranger than imagination, every answer opening a wider question, every distant signal reminding us that nature is more inventive than our first guesses.
It truly is the grandest reminder that reality still has surprises left. It's not simply far away, it's a testament to constant motion, change, and becoming in rhythms far older than any human concern.
The universe is vast beyond measure, but it is not still. It's a powerful thought to end on. If you found this discussion illuminating, consider sharing this episode with someone who might also enjoy it.